So Fabio, why is the testing so inconsistent in a nutshell?
Because the accuracy is low. For antibody testing, there is a high rate of false positives, and for the viral testing, there is a high rate of false negatives.
Since we haven't had a large sample group of the population to test yet, it really makes it the numbers are very mushy and soft. And so when people are like, oh, 20% of New York is infected, that's an estimate, and it's not a good one at that.
It's a very optimistic estimate.
Yeah. Okay. So then why does it have to be so complicated?
How do you mean?
I mean, why can't they get these tests accurate? Why can't they look at this thing under a microscope and say, hey, there it is. There's the virus. Chick, chick.
Well, they can. They can. The problem is that then there are issues with the way the test is performed, right? So the test goes through a number of phases, right? So there is a sampling in itself. So the person that samples need to be competent in sampling. The person that is being sampled, if they're congested, you're not going to pick the virus up because you're going to pick a lot of smudge, right? So there's going to be a lot of background noise. So then the sample is stored. If it's not stored well, RNA degrades very rapidly. So you might not pick it up for that reason. Then it's frozen. And then there is the analysis of the machine in itself. So, for instance, there is a lot of discussion about the Abbott test, which is the one that is also used at the White House, which is the most common viral test. Apparently, the machines are not really good. That's what I hear. And so there might be a fault with some of the machines. Because those tests are not being validated across laboratories, it's very, very difficult to get the correct picture.
Right. And then, as I understand it too, the virus is so small, you can't just go, oh, there's one viral particle, saw it on a microscope, test positive. You kind of have to grow it in a petri dish in order to really see it, right?
Well, you don't actually grow the virus itself.
No?
No, it's not real virus that you grow. What you look at, it's so first of all, you're right. To pick up a virus in a tissue is like looking from a needle in a haystack. And you need a high resolution electron microscope, and then you got to search and search and search until you find it. And you might find it right away, or it might take forever to find it. The test is actually run through an amplification process. So this is a nucleic acid amplification process. What we take is the genetic material for the virus. We extract that genetic material, which is RNA. We convert it to DNA, which is the RT-PCR piece. The RT means reverse transcriptase. So we translate that into DNA, and then the DNA is placed into a hot plate with enzymes that replicate that segment over and over again. And by replicating that segment, you actually have something that you can detect.
Got it. So that takes some time, and it takes some effort and
machines.
And there's another manufacturing process where there could be another accident or mistake happens in part of that process.
You might lose the virus or the viral genetic material across each of those steps, but if you see it, it's there.
The antibodies test gives a lot of false positives because
of the methodology again. It's an indirect methodology. It's an immunoabsorbent assay, or ELISA. So what that means is that from the serum, you take blood from a person, you take out the serum, and then in the serum there are proteins, and some of those proteins are antibodies. You put, to simplify it, you put the serum of this person in contact with a membrane that expresses the virus or the antigen that you're looking for in the virus. And if the antibody is there and it matches the antigen, it's going to bind to the membrane and it's going to give you a signal. Again, that doesn't tell you that the virus is there. In the best case scenario, it tells you that the immune system developed antibodies to that specific antigen.
Right.
But then you have antibodies that might be less specific, and therefore they would bind almost to anything.
So then you get a false positive.
And you get a false positive.
Got it. Okay, so I'm like, hey, well, why do we have these limitations? Why can't we get better tests? Why can't we get easier, more accurate testing?
Right.
Because biology is complicated, right?
Because biology is complicated.
It's just that difficult.
Yeah.
And I love how you said, like, the needle in the haystack with the viral test. It's just it's that small. It's just so tiny. I get this. Public officials or doctors, basically one person's saying this statistic and this other person using a different statistic. You know, why is there a discrepancy?
I don't know. I can't answer that, I'm afraid. I wish I could.
I was looking for an answer somewhere around the realm of, because statistics can be cut in a lot of different ways to prove what you want them to prove, especially when you don't really have an understanding of the numbers or an understanding of the big picture of what's going on.
Which is true, yes. I mean, by nature, statistics describes a probability. It doesn't describe a certainty.
Right, right.
So that is what the extrapolation that we are making. We are going from a probability into a certainty with no interface. It is actually interesting. One thing that is interesting is the majority of all of these antibody testing results are not being published on peer-reviewed in any way, shape, or form. They're all being distributed through press releases and through the media. So there is no vetting of the data whatsoever, and the majority of the data is actually not being portrayed by experts, but by politicians, by health officials, by people that actually doesn't have the understanding. Right. Remember the case of Riverside, those two doctors, they gave similar results, right? Oh, the virus is a lot more spread and therefore the mortality is very low. But they didn't give all the conditions associated to the testing procedures and to the probability of false positive and false negatives.
Right. And as you've explained to us, the numbers they were using were very soft numbers, and they tried to, and then they stated with authority that that means that a whole bunch of people have already had the virus and none of them died or even got sick, so we shouldn't worry about this.
Right.
And that's just a way overly bold claim, which a lot of people said that's an inaccurate statistic, bad statistics, and it's not considering all the testing and factors, and that's why it's a bad claim. It's
lulling us into a false sense of security.
And we don't want to be crazy and be all fearful about this, but we've got to be accurate. We got to be wise here. So all right.
This is the problem we're facing now. We're facing now a problem where states have reopened, right? On those assumptions, and now they are facing a resurgence because now the true infections are coming out. The true infections are hospitalization rates and death rates. So the hospitalization rate is the most concerning because that's a direct proportion of people that get infected. If we only think that 1% of people that get infected end up into hospital, it's very different from 7%, 10%, or 15%.
Yeah.
Right?
Yeah.
And that's why we are so unprepared.
Well, thank you, Fabio, for bringing more clarity to this issue for us.
I'm glad. I'm hoping that was clearer.